Hi, today I'm going to talk about Julia Gaussian Processes. This is an organisation, we normally refer to it as JuliaGPs. And the goal of the talk is to tell you who we are, what we're about, what we're trying to achieve, to give you an overview of the core bits of functionality that we're really dedicated to, an overview of the kind of non-core bits of functionality, which are the things that we've built on top of this core functionality. Often these are personal projects of the contributors, and the goal with them is to give you a flavour of the kinds of things you can use the core functionality to do, and to give you a sense of where we're trying to go with all of this, where we are at the minute, where we hope to be in a year's time. I think also I'd hope to give you a sense of how to navigate the organisation. There's quite a lot of packages in it now, and I really just want to make it clear how to approach them and what the important things are. So what I'm not going to try to do is give you an introduction to Gaussian processes. There's lots of fantastic resources for this floating around on the web. You can go to any of our packages, in particular abstract GPs or kernel functions, and find links to good resources on what a Gaussian process is. But for those of you who know what a Gaussian process is, just to let you know how I'm thinking about them for the sake of this talk. I'm thinking of a Gaussian process as a distribution over functions. So every time you sample from a Gaussian process, you get a function. For example, what's shown on the left here, with these thin blue lines. And we like them for various reasons. They're flexible and non-parametric. They don't come with particular parametric forms, so you can fit them to lots of different types of data. And exact Bayesian inference is tractable for small data sets, either when you don't have noise, as is shown on the right here. So on the right we've got the posterior distribution over the GP, which is itself another GP, given these 5 observations. And of course you can extend this in various ways, so these observations could have some noise associated with them and you could still be able to do inference. And when you move into regimes with lots of data or non-Gaussian observations, there are various sorts of approximate inference you can do and still do something useful. So if that didn't make any sense to you, I would suggest pausing the video here and going and looking at some other resources. So JuliaGPs, we're a collection of people who are interested in Gaussian processes. A lot of us are researchers, or they're specifically doing Gaussian process related things, or we're researchers who utilize GPs extensively, or we're researchers who utilize kernels in our work. There are various students involved in the organization and people like that. And that's really where we're coming from. So actually I'll just say in no particular order, there's me, my people's GitHub handles, I'm at the top, and then various other contributors, all of whom are fantastic and are just great to work with, so I'd like to thank them all. It's been a really enjoyable experience building this organisation with all of them. So we started out with the goal and continue to have the goal of creating flexible tools that are useful for our own research and GP research in general. We would also like to have, in addition to kind of the low-level functionality that you tend to need for that kind of work, high-level functionality that lets you have scikit-learn style fit-predict interfaces, so that someone who doesn't know the details of how GPs work but knows they maybe want some uncertainty associated with their predictions in a regression problem, can use the things we built. And we really want to have both worlds. We don't want to sacrifice one for the other. And the way we're doing that is by providing lots of points at which you can dive into our stack, and carefully documenting interfaces along the way, providing test utilities along the way. And so I should say, just at the outset, we're doing, I think, reasonably well at this first objective. This second objective is one of the places we're hoping for big improvements in the coming year. So in terms of the first objective, it's kind of worth off the bat saying what our core packages that I'm about to tell you about do not do. So they don't do things like parameter handling. So they don't let you build a model and then say optimize this model and change all the parameters in it in a kind of in a mutating way or anything like that. They just provide essentially a set of functions that accept the parameters you need in order to build a Gaussian process or to compute a log marginal likelihood or to sample random numbers, that kind of stuff, and assume that you're willing to cobble together a larger solution to whatever problem you're working on. So, for example, we assume that you're happy to work with things like OptimJL or Optimizers.jl or any of the kind of standard optimization packages. You're willing to work with parameter handling packages like parameter handling.jl or Flux's functors package or one of the various variants on these kinds of things in order to work with our GP functionality. So a common pattern you'll see throughout the ecosystem is we'll provide some GP functionality and then we'll provide an example that shows how to combine this with like Zygote and Optim and parameter handling to solve a standard problem. And the hope is that from there you can see where to go to solve your problem. And this again comes back to the kinds of users that we're currently targeting. We're assuming that you kind of know what you want to do, you know a bit about how to apply standard optimization tools, as opposed to use a fit predict interface in scikit-learn or whatever. So the core packages of the organization are these three: kernel functions.jl, abstract GPs.jl, approximate GPs.jl. And I would really recommend looking at them in this order, because abstract GPs depends on kernel functions and approximate GPs depends on abstract GPs. So just diving straight in, I'm going to give you an overview of what's contained in each of these packages, because there's not too much if you abstract away enough in any of them. So kernel functions has two things. It has an abstraction for kernels, and then it has a bunch of kernels. So the abstraction, we've got an abstract type called kernel, on which we define a pretty straightforward interface. It's essentially two functions and also their mutating versions. So kernel matrix takes a kernel, takes two collections of inputs, and returns the corresponding kernel matrix. Kernel matrix diag does the same thing as kernel matrix, but it only returns the diagonal. And that's needed for computational reasons. For example, in abstract GPs, it's really important to be able to just compute the diagonal of the kernel matrix. The other thing we do is provide test utilities for this interface. So the interface is defined both in the docs and implicitly via these test utilities. So if you make a new subtype of kernel as a concrete type that you can instantiate, you should use these test utilities on it to check that it's implemented all the functionality we expect it to have implemented, and by extension that downstream packages like abstract GPs and approximate GPs will expect it to have implemented, that it does so consistently. So for example, that when the kernel matrix is meant to be symmetric, it's actually basically symmetric. That if you ask for the diagonal of kernel matrix, you get the output of kernel matrix diag, stuff like that. And then, as I said, we provide a lot of kernels. Standard things like squared exponential kernel, matern kernel, or various matern kernels. Standard combinators for kernels that produce other kernels. So addition, you can take two kernels, add them together, get another kernel. You can associate a length scale with a kernel. So that's one thing I should point out that we do differently from other places. Often in other packages, you'll make a squared exponential kernel, and it'll kind of assume you want a length scale with it. We don't do that. We assume your length scale is 1, and then we say, okay, well, if you want a length scale, do it. And that just reduces a lot of the code we have to write, essentially, and makes everything more modular and makes it more transparent as to what's going on. And I should say that all of these kernels, we test them using our test utils. Like we use this interface here extensively to implement all of these things. So if you want to implement your own kernel, you should just use these test utils like that. They're exactly what we do. And if you want to implement your own kernel and then you want to contribute it back to kernel functions, please open a PR. And if it's not a really, really obscure kernel, we'll probably accept it. So that was kernel functions, and now abstract GPs, which builds on kernel functions. So it does a pretty similar set of things to kernel functions, just at a higher level of abstraction. So it provides an abstract type, abstract GP. It provides a few interfaces on abstract GP. I'm not going to go into any detail on these, except to say that the primary interface is what we expect people who consume a GP to work with. So for example, we try and use the primary interface in approximate GPs. That contains the functions that people generally want, like the log PDF or the log marginal likelihood of a GP at a load of locations, observing some observations at those locations, or RAND, like sample the GP at a bunch of locations, as opposed to compute the kernel of the GP at a load of locations. It's pretty rare that you actually want to do that. Normally you compute that covariance or the kernel for the sake of generating random numbers or computing log marginal likelihoods. So the primary interface doesn't include that, and that's really important for a variety of scalable approximate inference techniques. So we've written quite extensive docs on these three things, and we've got associated test utils for each of them. So I'd really suggest going over to the abstract GPs repo and reading them, taking a look at the test utilities. If any of it's not clear, again, please open issues. And then, so as with kernel functions, we implement a concrete GP type, which utilizes these test utils. It implements the internal interface, which means that it also implements the primary and secondary interfaces. This is your kind of basic GP type. It's your go-to GP. It has a mean function and a kernel from kernel functions JL. And it can do all of the standard things you'd expect a GP to do. The last thing this package has is some convenience functionality, things like plotting recipes, stuff like that. That kind of falls in the miscellaneous things. The important things are the abstract GP type and the fact that there is a concrete GP implementation. So the last package is approximate GPs JL. So this is the most rough around the edges package of the core packages. It's currently being actively developed. It's got a couple of things in already, kind of standard scalable algorithms for working with large data sets, pseudo point methods, also known as sparse methods, inducing point methods, things like that, inducing variable methods. And it's got standard algorithms for working with non-Gaussian likelihoods, variational inference, Laplace approximations, things like that. The scope of the package is really standard approximations for these settings. So we're not trying to implement necessarily the latest thing that appeared at a NeurIPS paper. We want the standard set of tools that if you're a GP researcher, you're going to want to benchmark against, or if you're a user of GPs, other things that you would reach for, or that we would suggest you reach for as a first port of call for your problem. It's not quite clear where we're going to draw the line on this yet. That conversation's ongoing. And as I say, we're hoping to see a lot of improvement here over the coming year. So I should just briefly note how what we're doing in JuliaGPs compares to what's going on in Gaussian Processes.jl. So Gaussian Processes JL existed before our work in JuliaGPs, and it feels a lot like a traditional Gaussian process package. So if any of you have used MATLAB's famous GPML package, it's a lot like that. And the reason it wasn't sufficient for us is kind of what I've discussed already in terms of what our objectives are, is that it's hard to kind of go in at any particular level and do the things that you want to do with it as a researcher. And it's not compatible with reverse mode AD. And that's really, really something we needed. So finally, I'm going to talk through some of the non-core packages. These are the kind of the downstream packages that are either personal projects of people in the organization, or are just projects that are derived from these core packages. From the perspective of users of packages in the organization, you should expect less support if you're using these packages than you should expect if you're using the core packages. The core packages, everyone in the organization is committed to maintaining to some degree. And so you can expect quite quick response times to issues and stuff like that. Whereas these packages, as I say, some of them are just personal projects, or they're like package for my paper kinds of projects. So you can generally expect less support. And when you're starting to, if you want to use them in your work, you should consider that and maybe open an issue to see if that you get a response, that kind of thing. So the first package I'd like to thank Theo for making. So this implements some of his work on fast approximate inference for non-conjugate, non-Gaussian likelihoods. So you can see the relevant paper at the bottom. And this package, implements that paper, and it implements tools for building the kinds of approximations that I described in that paper. It's got good docs, it's got lots of examples, and it's fast. I'd like to thank Stefan for this example. So this is GP-diffie-Q-JL. And again, you can consult the relevant paper at the bottom if you're interested in it, or go to the repo. The purpose of this package is to use GPs to specify dynamical systems. So if you have an ODE of the form of the one here, so the time derivative of the state being some function of the state, the purpose of this package is to let you place a GP prior over this function of the state, and then to do inference in that GP based on observations of the system. And as Stefan kindly pointed out to me, the benefits of this are that you can include symmetries via the kernel, and you can get uncertainty estimates for extrapolation. So if we look at the example on the right here, the black dots are observations, and when you can propagate the uncertainty you have about f through the predictions that the system makes further forward in time. So you can see the error bars inflate as you go forward in time. A package maintained by Invenia is linear mixing models.jl. And so this contains a collection of standard multi-output GP models. In particular, it contains the orthogonal independent linear mixing model, which was introduced by Wessel Bransma in this paper from 2020, which work I was also involved in. And the benefit of the Euler-Mem is that it scales to really large numbers of outputs. So usually Gaussian processes for multiple outputs have a really hard time if you have lots of outputs, but the Euler-Mem is set up in such a way that it's not an issue. And you can see that over here that You can use, say, maybe 200 outputs and have lots of latent processes, and it still works fine. Seno.jl is a package that has been around for a while. It actually predates the ecosystem, but has been refactored and had lots of code taken out of it and really, really simplified since the version that was presented at JuliaCon a few years ago. And so it's designed for working with collections of GPs. So if you take a look at the code snippet on the left here, you'll see GP floating around in lots of places. So what this is doing is setting up a load of GPs and then saying how they all relate to one another. And the example here, I've used it to produce a model jointly for global CO2 and air temperature. So on the top, you can see the kind of the classical Keeling of the Mauna Loa CO2 data, and on the bottom here, you can see temperature observations up to the mid-90s. So they're these blue dots. So the task here is this kind of standard thing you might want to do in climate, which is saying, well, if you had, say you were in 1995, and you had some idea of how much CO2 was going to be emitted over the next 25 years, maybe because you're like the IPCC or someone and you're trying to do scenario planning for, well, how much, if we emit this much, what happens? And then the point is to ask, well, what happens to global average temperature? And the model has successfully managed to pick up on the fact that that CO2 and temperature are coupled based on the data from the 50s through to 1995, and then it predicts through into the future. I should say this, fairly toy example, but I was pleasantly surprised at how reasonable the predictions look. You can find more examples like this in the repo. The last package I'll talk about is temporal GPs. So this is one of my packages that I used in some of my work, the reference at the bottom. And it's useful for working with GPs involving time. So the goal with this is to make GPs involving time really scalable. So be able to work with lots of observations. And it's essentially a one function API package. It takes a GP from abstract GPs.jl associated with the name fnaive here. And then you call a function on it to SDE, which really just gives it some extra metadata that says, yes, this is a GP that I would like you to treat in a particular way and to try and do inference on it in a particular way that is really scalable. And you also have to give it some more information about what kinds of ways you want to store certain things. But the important thing is you take a GP from abstract GPs and you say, try and do inference in a particular way. And so the thing this toSDE function outputs is another subtype of abstract GP. And so it implements the primary abstract GP's API. And over here you can see that the scalability. So the blue squares are how long it takes to compute the log marginal likelihood of a capital G GP. And you can see it scales quite poorly as the number of observations n increases. So by the time you're at 10,000, it already takes, say, 10 seconds on my computer. But if you use temporal GPs, in this case, you can compute the log marginal likelihood on like 1 billion data points in maybe 15 seconds or something like that. So now that I've given you an overview of the kinds of things we've done with the abstract GPs ecosystem, with Julia Gaussian processes, I want to talk about what I think we're currently doing well at, or reasonably well at, where we're not doing so well and where we'd like to improve over the coming year. So I think we do have pretty good tools for research at the moment. If you're a GP researcher, I think, or I hope you'll find something useful in the ecosystem. And I'd say we also have pretty reasonable tools for knowledgeable users. if you know what a loss function is, how to use Zygote, how to use optimizers JL or Optim or whatever, and maybe you've seen a tutorial on what objective function to use with the GP, you should be able to see what's going on in the ecosystem, follow through some of the examples, and cobble something together that can solve your problem. I think our testing and our testing utility functionality is pretty good. I think our testing is good because of our testing utility functionality. We've really tried to standardize where we can. Everything we do is on the CPU. The fact that we're doing well on the CPU is suggestive of the fact that we're not doing so well on the GPU at the minute, and we'd like some help. We're doing well on the AD compatibility front. We're Zygote compatible. Presumably we will be Diffractor compatible. And also we've got various utilities, which I'm pretty pleased with, things like plotting recipes, that kind of stuff. So where we'd like to go, we really want better tools for kind of scikit-learn style, fit-predict, out-of-the-box data science. As I've alluded to, we currently support researchers and people who know a reasonable amount about how to do machine learning and statistical inference, but we don't provide that kind of scikit-learn style interface, and that's one thing we'd really like to improve over the next year, and is where we'd really like some help. As I alluded to previously, we really could do with some help on the GPU front. It's a pretty straightforward pathway. We know what we need to do. We just haven't had the chance to do it. We don't have the time to do it. I think this would be a really good thing for someone who is keen to, who's maybe done a bit of Julia. I don't know that you even need to know much about Gaussian processes to be able to help us. The main things we need help with are like setting up CI, getting some basic tests running, just getting the basics running and getting the ball rolling, and then things should start going quite quickly. We always want to improve our testing, so I've put that here as just a matter of principle. We want to get much further along with approximate GPs and figure out what feature completeness looks like and achieve it. And also, I just showed you 5 packages that use the Julia GP's ecosystem to do things, and I'd encourage you to take a look at them. We want to see more of that. I imagine I'll continue to produce more random packages that do things using GPs. It'd be great to see more researchers and people building more projects using Julia GPs. So please come and join us. We're all on the Julia Slack. Maybe message me directly if you're keen to get involved, and or come over to GitHub at Julia Gaussian Processes and get involved. So I'd just like to say thanks to Invenia Labs, my employer, the Cambridge Machine Learning Group, my until very recently research group, and in particular my supervisor Richard Turner, and all of the collaborators who sent me content for this presentation. It made my life much easier. Thank you.